Have you ever wondered how databases maintain data integrity and reduce redundancy? Let's talk about a systematic process known as database normalization, which plays a crucial role in organizing data in a way that ensures data integrity and minimizes redundancy. This process is all about organizing tables and reducing two key issues: dependency and anomalies. In essence, the goal of normalization is to create well-structured relations that minimize the possibility of data inconsistencies and improve data integrity. But how does this process work? Well, normalization typically involves several stages, each of them addressing specific types of anomalies. Throughout this journey, we will explore the fascinating world of database normalization, starting from the first normal form, or 1NF, all the way to Boyce-Codd Normal Form, also known as BCNF, and even beyond. In the next few minutes, we will embark on the fascinating journey of database normalization, from 1NF to BCNF and beyond. So, what's the first step in database normalization? It's called the first normal form, or 1NF. Now let's dive into the heart of 1NF. The essence of this form is all about atomicity. In the world of databases, atomic means that each attribute or column in a table should contain values that cannot be further divided into smaller parts. Think of it as the indivisible building blocks of your data. For example, a name attribute should not contain both first and last names. Rather, it should be divided into two separate attributes, first name and last name. But atomicity is just one aspect. The 1NF also insists on single-value attributes. That is, each attribute must have a single value for each tuple or row in the relation. So if an employee has multiple phone numbers, you don't just cram them all into one cell. Instead, you create separate rows for each phone number, keeping the employee's other details consistent. Now here's where it gets a little more intricate. 1NF also targets the elimination of repeating groups and nested relations. To achieve this, you need to organize data into separate tables, each with a primary key. A primary key is a unique identifier for each record in a table. For instance, an employee ID could serve as a primary key in an employees table. By doing this, you're essentially breaking down a complex table into simpler, well-structured ones. This not only makes your data more manageable, but also reduces redundancy and the risk of anomalies. To sum up, the first normal form is about ensuring atomicity, single-value attributes, and the elimination of repeating groups and nested relations. It might seem a little daunting at first, but once you get the hang of it, it's a powerful tool for organizing your data efficiently. Achieving 1NF is the critical first step in the normalization process, paving the way for the subsequent normal forms. Once we've achieved first normal form, or 1NF, we can proceed to the second normal form, or 2NF. So what does it mean for a relation to be in 2NF? Well, there are two main requirements. First, a relation must already be in 1NF. Second, every non-prime attribute, meaning attributes that are not part of any candidate key, must be fully functionally dependent on the entire candidate key. Now let's break that down. Full functional dependency means that if we have a composite key, which is a key made up of multiple attributes, every non-prime attribute must depend on the whole key, not just part of it. In other words, if you change part of the key, the non-prime attribute should also change. If it doesn't, then we have what's called a partial dependency, and that's a no-no in 2NF. So, what do we do with these partial dependencies? We decompose or break down our relation into smaller relations. Each of these new relations will have its own key, and the non-prime attributes will fully depend on that key. By doing this, we're ensuring that every non-prime attribute depends on the entire primary key, rather than just a part of it. This process of decomposition can seem a bit daunting, but remember, the goal here is to reduce redundancy and improve data integrity. By making sure that all non-prime attributes fully depend on their respective keys, we're ensuring that our data is consistent and reliable, which is the whole point of normalization. But don't worry, we're not done yet. There's still more to learn about normalization, and the journey continues with the third normal form, or 3NF. But for now, let's take a moment to appreciate the elegance of the second normal form. It's like a well-crafted puzzle, where each piece fits perfectly, contributing to a larger, well-structured whole. 2NF builds on the foundation of 1NF, further reducing redundancy and improving data integrity. It's another step in our journey towards a well-structured, efficient, and reliable database. So stay tuned as we delve deeper into the fascinating world of database normalization. Having achieved second normal form, we can now move on to the third normal form, or 3NF. The transition from 2NF to 3NF involves a deeper understanding of the relationships between our data attributes. In 3NF, we aim to eliminate any transitive dependencies that may exist in our tables. So what is a transitive dependency? Imagine we have a table with attributes A, B, and C. A transitive dependency occurs if A determines B and B determines C. In this scenario, C is transitively dependent on A through B. In 3NF, we want to ensure that every non-prime attribute, which is an attribute not part of any candidate key, is non-transitively dependent on the primary key. To achieve this, we decompose relations with transitive dependencies into separate tables. The goal is to ensure that every non-prime attribute depends only on the primary key and not on other non-key attributes. This decomposition reduces the risk of anomalies and inconsistencies in our data. Let's illustrate this with a simple example. Suppose we have a table that stores information about books, including the book's ISBN, title, and author's birthplace. In this case, the book's title is functionally dependent on the ISBN, and the author's birthplace is dependent on the book's title. This creates a transitive dependency, which violates the rules of 3NF. To resolve this, we can divide the table into two. The first table contains the ISBN and title, while the second table links the title to the author's birthplace. Now, all non-prime attributes in each table depend directly on the primary key, adhering to the principles of 3NF. Remember, the purpose of 3NF is to further enhance the structure of our database by reducing redundancy and dependency. It's like tidying up a room. The more organized it is, the easier it is to find what you need. 3NF takes us one step closer to a well-structured, redundancy-free database schema. But normalization doesn't stop at third normal form. Let's explore Boyce-Codd Normal Form, or BCNF, and beyond. BCNF is a stronger version of third normal form, addressing a specific type of anomaly not covered by 3NF. For a table to be in BCNF, it must already comply with the rules of 3NF. However, BCNF introduces an additional requirement. For every non-trivial functional dependency X, X must be a superkey. A superkey, for those who might not know, is a set of one or more attributes that, taken collectively, allow us to uniquely identify a tuple. A candidate key is a minimal superkey, meaning it has no redundant attributes. In BCNF, every determinant must be a candidate key. If a relation violates BCNF, it's time for some more decomposition. We'll need to break it down into separate tables to eliminate the anomalies related to non-trivial functional dependencies. This process helps maintain data integrity and reduce redundancy. But hold on, we aren't done yet. Yes, there's more to normalization than BCNF. Although BCNF addresses most common types of anomalies, some situations require even more stringent forms of normalization, such as fourth and fifth normal forms. Fourth normal form, or 4NF, deals with multi-valued dependencies. It ensures that records do not generate unnecessary data combinations. Fifth normal form, or 5NF, also known as project join normal form, deals with cases where information can be reconstructed from smaller pieces of data that can be maintained with less redundancy. It's worth noting that these higher normal forms are less commonly used than their predecessors. They come into play in very specific scenarios where the data has particular characteristics. In summary, normalization is a powerful tool in database design, but it's not a one-size-fits-all solution. It requires careful analysis and thoughtful application. And remember, while it may lead to a larger number of tables and more complex queries, the ultimate goal is to improve data integrity and reduce redundancy. BCNF and beyond help us address more complex types of dependencies, further improving data integrity and reducing redundancy. So that's the process of database normalization in a nutshell. We've journeyed from the first normal form, which focuses on breaking down data into its most basic, indivisible units, all the way to the Boyce-Codd Normal Form, a more stringent level of normalization that deals with complex functional dependencies. Beyond BCNF, we have even more advanced forms like the fourth and fifth normal forms, addressing intricate dependencies like multi-valued and joined dependencies. The goal of all these steps? To create a database that's free from redundancy and anomalies, with improved data integrity and consistency. But remember, while normalization is crucial, it's also key to balance it with performance considerations. Too much normalization can lead to a large number of tables and complex queries, which could affect performance. Remember, normalization is not an end in itself, but a means to achieve a well-structured, redundancy-free and efficient database. Until next time, keep exploring the fascinating world of databases.